Good morning, students. So today we will solve one more numerical on module number 3, vapor power cycles. So this is numerical number 6. So this numerical problem I have taken from VTU question paper June-July 2015, 15 MA 43, that is CBCS scheme, and question number 3B. So first we will read the definition of the numerical or problem. So in a steam power plant operating on ideal Rankine cycle. So the first line indicates it is not actual Rankine cycle, it is simple Rankine cycle or ideal Rankine cycle. So here we will not consider any losses in the turbine or losses in the pump. So next line, steam enters the turbine at 20 bar with an enthalpy of 3248, that is 3248 kilojoule per kg, and an entropy of 7.127 kilojoule per kg Kelvin. The next point, the condenser pressure is zero point 0.1 bar. So this is the pressure P2. Find the cycle efficiency and specific steam consumption. It should be in kg per kilowatt hour. And one more condition he has given, do not neglect pump work. So in some of the numericals, we may ask you to neglect the pump work and calculate Rankine efficiency. Why it is this? The compared to the turbine work, that is work done by the turbine, is much greater than work done on the pump. So if you consider, like, for example, 2000 kilojoule per kg, it is an work done by the turbine, and the work done on the pump is approximately 3 to 4 kilojoule per kg. So for this case, the work done by the turbine is much greater than work done on the pump. So you can sometime neglect the pump work and calculate efficiency also. But here clearly he said do not neglect the pump work. So you will calculate pump work and we will consider and calculate the efficiency of the Rankine cycle. So as we discussed in the numericals in the previous lectures, so in the numerical in the problem he has to give minimum 3 conditions. One is boiler pressure, that is the maximum pressure in the cycle, and second one is condensation pressure, that is the minimum pressure, that is 0.1 bar he has given here. And one more condition he should give is the quality of steam or condition of steam at inlet to the turbine or at exit of the turbine. But here, which condition? The third condition, that is condition of steam at enters the turbine, that is inlet to the turbine is 20 bar. This is a maximum pressure. And one more condition he has given. The enthalpy and entropy of both properties he has given at inlet to the turbine. So, but he has not mentioned specifically whether it is a superheated steam or it is a dry steam or it is a wet steam at inlet to the turbine. He has given the enthalpy value, but he has not given any word dry or superheated or wet. Then the question is how to identify which case it is, whether superheated steam is entering to the turbine or dry steam is entering to the turbine or wet steam is entering to the turbine. Okay, this is the question, but we'll make it clear. So to avoid such confusions, so what you have to decide is just look at the enthalpy value what he has given, 3248 kilojoule per kg, that is 3248. So this value you have to compare with enthalpy of gas, that is Hg at 20 bar. I will repeat it again. At 20 bar, note down the value of Hg from the steam table. Hg is nothing but enthalpy of gas, that is called dry steam. Okay, the value of Hg at 20 bar, if it is less than the given enthalpy, then it is superheated steam. For example, so you will take the value of enthalpy from the steam table at 20 bar. So this is the value 2797.2, that is 2797.2. But given enthalpy is how much? 3248. The given enthalpy is greater than the value of enthalpy from the steam table at 20 bar. So that the condition or the quality of steam which is entering to the turbine is superheated. Again, question: how on what basis you have decided? Only by the basis of these two numbers? No. For example, I will make it clear. Listen carefully. So if you supply 2797.2 kilojoule of heat to the boiler at maintaining 20 bar pressure, then the steam will become dry steam. But he has supplying more than 2797. How much he has supplied in the given problem? 3248. Understood? The minimum value of heat required is 2797.2 to convert water to dry steam. But in the numerical, the given condition is 3248. So extra heat he has supplied. Okay, 400 to 500 extra heat he has supplied to the boiler at 20 bar, so that the steam will become from dry steam to superheated steam. That is the reason it is a superheated condition numerical. Here we have written the given enthalpy is greater than the enthalpy from the steam table at 20 bar, hence it is superheated condition at inlet to the boiler. Sorry, inlet to the turbine as well, or exit to the boiler. Okay, so we will draw the TS diagram for the superheated condition. So this is the TS diagram for superheated condition. So point number 1 is inlet to the turbine, point number 2 is outlet of the turbine, and point number 3 is inlet to the pump, and point number 4 is inlet to the boiler or exit of the pump. So 1 to 2 is expansion, 2 to 3 is condenser, heat is rejected to the surrounding, and 3 to 4 is work done on the pump. So step number 1, we will write the given data. So boiler pressure, we will take it as P1 20 bar. So at 20 bar, you note down the values what he has given. So H1 he has given 3248. Why I have taken H1 is clearly he said at inlet to the turbine. Steam enters the turbine at 20 bar with an enthalpy of 3248. So it is inlet enthalpy. Similarly, he has given the entropy also. So both we have written here, and one more condition, that is condenser pressure P2 is zero point 0.1 bar. And what he has asked, find efficiency of the Rankine cycle and SSC, specific steam consumption. So this is step number 1. So step number 2, properties of steam from steam table book or data handbook. Dear students, so note down the two pressure values. So at 20 bar, you note down all the properties, and at same time at 0.1 bar you write down all the properties of the steam. So here, so whatever the properties you will see at 20 bar you have written here, and at the same time 0.1 bar also we have listed here. Okay, so step number 3, find enthalpy at each point, that is 1 2 3 4. If you look at the TS diagram, so you'll find the enthalpy at point number 1 2 3 4, because these are the values required for calculating the efficiency of the Rankine cycle. Okay, again we'll look at into the equation. Step number 3 will continue. So efficiency of the Rankine is equal to work done by the turbine minus work done on the pump divided by heat supplied. The difference between the two works we can also call it as net work done, and heat supplied as it is. I have taken equation number 1. For clear purpose, for our understanding purpose, again I have taken TS diagram here. It is not necessary to represent TS diagram once again. Only for explanation purpose I have taken TS diagram once again here. So 4 to 1 is boiler, And dear students, keep in mind point number 4 starts from boiler, and at up to point number 1 it is boiler only. Okay, so that is the reason 4 to 1 I have written boiler 20 bar. It same is constant pressure process, because in the boiler we are adding constant pressure, heat addition. So work done by the turbine is equal to m dot h1 minus h2. Again equation number 2. Has he given value of m here? No, he has not given mass flow rate of steam, so I will not consider m here. I will take m is equal to 1. But h1 and h2, h1 is given directly in the problem. In the numerical given condition he has given, that is superheated steam, if it is here. So for example, if the value of enthalpy given in the problem is 2772, for example here 2792.2, this is the value of enthalpy at gas. Gas is nothing but it is dry steam. If this is the value is given, we will consider it as dry steam condition. Instead of taking 1 to 2, I could have taken from this point. But the given enthalpy is more than 2772, that is 3428. That is the reason it is superheated condition. So H2 is equal to, what is H2? Enthalpy at point number 2. So point number 2 is which pressure? It is condenser pressure here. So H2 is equal to HF2 plus X2 into HFG2. So for your purpose, I have written here H2 is equal to, because I am taking enthalpy at point number 2 here. So from here to here it is H2. So H2 is equal to this enthalpy, that is HF2. Don't look at the point number 3 now. You look at only point number 2. So from here to here it is HF2, because it is a water region. Enthalpy of fluid at point number 2. That is our second pressure. Similarly, between these two, saturated liquid line and saturated wetted line, we will take it as enthalpy of mixture of both fluid and gas, that is HFG. What pressure? At pressure 2, and we are taking from point number 2 also. So here HF2 already we have written, we have taken data from steam table book, that is HF2. HF2 is 0.1 bar. We are taking it second pressure. So 0.1 bar, what is the value of HF2? 191.8. Similarly, HFG2 is 2392.9. So look at these values. These two values will be substituted in the equation number 2 here. So H2 is equal to HF2 I have substituted. I don't know the value of X2. Write it as it is, because he has not given in the condition or in the numerical data. And HFG2 is at 0.1 bar. We have taken the values. But unknown is X2. And we know that 1 to 2 is isentropic expansion process. Isentropic process. So during isentropic process, S1 is equal to S2. Here again, S1 is equal to S2 you have written. So S1 is the entropy at point number 1. It is given in the numerical, and the given in the problem also. Directly you have written here. Again, S2 is equal to same formula what you have written for enthalpy, you written for entropy at point number 2. Only in place of enthalpy, it will become entropy. Yes. So SF2 values also we have listed at 0.1 bar in the given data. Step number 2. So we have written the values X2 as it is, SFG2. So in this equation, the only unknown is X2, and doing some mathematical operations, calculate X2, that is 0.864. So what does it mean? 86%, 86.4% is steam, remaining is water. So that is the reason. So point number 2 is nearer to water. So if it is percentage of water is more, it could have been nearer to the saturated dry line, saturated wet line. Sorry. Okay. Next, once you calculate the value of x2 using equation number 2, substitute H1 minus H2, then calculate work done. So because M is equal to 1, he has not given in the problem. So H2, I have written here, we have calculated H3 is equal to HF2. Why H3 is equal to HF2? Please look at the TS diagram. So this is H3. From H3 to left side, this is HF values. Point number 3 is located on wet line. That is the reason you will represent with HF. So I need to calculate H3. So H3 is equal to HF. But at what pressure? Second pressure. So HF2. Understood? Point number 3 is located on wet line, that is saturated liquid line. This is saturated liquid line. So any point which is located on saturated liquid line and the property at that point will be represented with the suffix F because it is fluid region. Fluid is nothing but water region. So enthalpy means HF, entropy means SF. So now I need to calculate H3. So H3 is equal to HF3. Okay, 0.3. But at what pressure? It is at zero point 0.1 bar pressure, condenser pressure. So here H3 is equal to HF2 is equal to 191.8 kilojoule per kg. Here written here 0.223 is constant pressure process in the condenser. So HF2 is equal to HF3, both are same because zero point 0.2 as well as zero point 0.3 are zero point 0.1 bar pressure. So sorry, zero point 0.2 bar, zero point 0.1 bar, whatever may be the pressure. Here it is 0.1 bar, sorry, 0.1 bar. Now both H2 and H3 you have calculated. So the remaining one H4. So H4 is equal to, look at the TS diagram. It is very easy. Okay. Now here from this origin to H4, this is the value of H4. Okay. So H4 is equal to H3 plus work done on the pump. From 3 to 4, this length of the line indicates work done on the pump. And from here to the x-axis indicates H3. So H3 plus WP is equal to HF4. So H4 is equal to H3 plus work done on the pump. So work done on the pump is not given directly in the problem, but we know the equation. Work done on the pump can be calculated using this equation, difference in pressure into specific volume of fluid. So why you can take, sir, specific volume of fluid, why you are not taken specific volume of gas? Dear students, it is easy. As we know that pump is handling working fluid is what? That is water. So if the pump inlet condition is gas, we could have taken VZ, but here in the given condition, so point number 3 is located on water line, that is liquid line or wet line. So here it is water. So VF we have taken specific volume of fluid. So pressure is 20 bar. 20 bar is 1 bar is 10 to the power of 5. So 20 into 10 to the power of 5 minus zero point 0.1 bar is the second pressure. So 0.1 into 10 to the power of 5. So VF value we have written here, that is at 0.1 bar. So after doing this calculation part, we'll get the value of WP 2.01 kilojoule per kg. Substitute the value of WP in this equation. So 191.8 plus 2.01. So add these two, you will get H4 value. Now you have calculated all the enthalpy values H1, H2, H3, H4. Now using equation number 2, as I explained you in the equation number 2, calculate work done. Wt is equal to m is 1 kg. He has not given in the numerical. In the previous problem he could have given 9.5 kg per second. In the lecture number 5, numerical 5, you have taken m is equal to 9.5 because he was given the given data, but here he has not given any data related to mass flow rate, so we'll assume it as 1. This is h1 value, this is the given value, minus h2 value. So subtract these two, you will get 989.7. So why he has given on condition, at the given condition he has given here in the definition of the problem, do not neglect pump work. But in some of the numericals, he has given and he will ask to calculate efficiency of the Rankine cycle with neglect pump work. Neglect pump means the reason is the work done by the pump is less compared to work done by the turbine. For example, you can see here work done on the pump is 2.01, but work done by the turbine is 989. There is much difference between these two. If you subtract 989.7 minus 2 is 987. So if you add also, it doesn't make much difference. So that is the reason you can neglect the pump work whenever he said. Okay, but here specifically as asked, do not neglect. So I will consider in calculating net work done. So net work done is equal to Wt minus Wp. So this minus 2, 987.3. Okay. So these values, once you calculate these values, does not match with exact values or with your calculator, with your answers. So almost all it will be nearer to the answers. Okay. So now heat supplied is a one more data you need to calculate. Heat supplied in boiler, that is 4 to 1 process, 4 to 1 m dot h1 minus h4. Why we taken h1 minus h4? H4 is the point located at top of the TS diagram, and H4 is the point located at bottom of the diaphragm. So between these two, point number 1 enthalpy is more compared to point 4. That is H1 minus H4. So m dot is not given, mass flow rate of steam not given. So you assume it as 1 kg per second, and H1 is given, the given numerical H1, and H4 you have calculated. Subtract these two, you will get the value of QS3054. So from equation number 1, efficiency of Rankine cycle is net work done divided by heat supplied. Net work done is, you have calculated, that is 987.3. That is you have substituted here. So heat supplied is, you have taken 3054.1. Substitute here. So ratio of these two, the efficiency is 32.32. So you make it 0.32. That 0.32 will be converted into percentage, 32.32. The maximum efficiency of the Rankine cycle is up to maximum is 50%. It should not exceed more than 50. So on an average, the efficiency of the Rankine is 35 to 45. So due to some calculated mistake, if the value of efficiency, if it crosses 70, 80%, assume that somewhere you have done mistake. So then last unknown data, what is as step number 4, specific steam consumption, that is mass flow rate of steam divided by work done by the turbine. Mass flow rate of steam is not given, so assume that it is 1, multiply by 3600 is in the given numerical. He has asked put in terms of kg per kilowatt per hour. Here, read the problem once again. Specific steam consumption in kg per kilowatt hour. So if you are not multiply by 3600, it will be kg per kilowatt second. So to convert seconds into 3 per hour, so multiply by 3600. Here we have multiplied. Then divided by same net work done by the turbine is 987.3. Okay, so SSC is 3.65 kg per kilowatt hour. So this is one type of ideal Rankine cycles. In the next lecture, we will come with one more VTU question paper problems. So it will be asked for 10 marks. So thank you so much.